Bismillahirrahmanirrahim. I am Muhammad TALAL, and this is the hardware demonstration part of the final year project, which is the dual axis solar tracker. Now I will begin the explanation of the project by first outlining and telling you all about the mechanical structure of the device and how it helps in the 2 degree of freedom motion of our solar panel. So basically, first you should know that our project was a dual axis solar tracker, the purpose of which is to keep this solar panel aligned at an angle of 90 degrees with the sun rays. Now for the purpose of that, we first had to build a system which could keep the solar panel within itself, very much like this system, and rotate it at 2 degrees of freedom around 2 axes so that it could keep itself at an angle of 90 degrees from the sun rays. Now for that, you can see that what we first had to do was create this rectangular frame, this one, which is all the frame that you see here. It has been colored mustard but is actually made from iron bars. You can notice the welding at the edges like this and this. These are all welding spots, so you can be sure that it has been made of metal, not wood, and it was all welded here in my home. So this is the rectangular frame in which the solar panel has been fitted using nuts and bolts. As you can see here, these are the nuts and bolts at both the top and the bottom. Now this frame itself sits on these bearings. Now this shaft that you see was also specially made to fit in a bearing of this side. Now the purpose of these bearings and this design is to reduce the torque required by the motors to rotate the panels, because you see this way the panel rotates about its own axis. And when that happens, the only thing that is stopping the rotation is the bearing friction, which is very, very minimal. So we can rotate the panel with little to no energy at all. Okay, so this rectangular frame stands within this U frame, and that U frame is connected to this base. Now for this base, this is the worm gear assembly, this is the DC motor, and this is the part of the base which actually rotates the entire solar panel on the Z-axis. Now for this, we have used this chain so that it connects this worm gear assembly with the U frame of the solar panel structure, and it has a ratio of about 1:20, so it increases the torque as well and decreases the speed of rotation, which is good for us. Now the purpose of this worm gear assembly is to stop the solar panel from rotating freely about this axis. You see, when I apply force right here on the Z-axis, it doesn't move. You can see that the entire bottom of the frame is moving, but it's not rotating. It's moving because obviously it hasn't been bolted down here. Okay. Now this was the rotation for the Z-axis. I've already explained in detail the purpose of this worm gear assembly. It has a mechanical feature which states that the shaft cannot drive the worm. So the solar panel, this little movement of the solar panel, this is the internal play of the worm gear assembly. This little movement is there. It's a mechanical fault. We couldn't do anything about it. Now similarly, another worm gear assembly has been used for the other axis rotation. This is the solar panel again. This is the worm gear assembly for the X or Y axis rotation, whichever, depending upon however you have chosen to orient your axis. Again, now this shaft is directly connected to inside of this worm gear assembly, so that when the motor rotates, this panel can move in this direction. Now as you can see, I'm applying force here and the entire frame is moving, but the panel is not rotating about this worm gear assembly. There's little play like from the play that was in the assembly that rotates the entire frame about Z-axis, but it basically locks itself in whichever position the motor decides that it should be in. Okay, so this was the mechanical frame that was designed for the 2 degree of freedom motion about z and x axis. Now the other components which aid and basically make our system intelligent and form the part of our mechanical structure. This little thing right here is basically our version of an anemometer. We have modified a flow sensor with this part that we made entirely out of PVC. We cut 2 circles from PVC, and then these blades were cut from PVC as well. They were joined together, and then it became this, which basically moves with the wind. And this is a Hall effect sensor, so when this moves, you see this little white thing here. It's connected to a magnet, which creates the change in the magnetic field of the sensor, and we notice the speed of the wind. We have calibrated this to give us a value of flow which is in liters per minute at the wind speed at which we want our panel to make itself horizontal and stop. This part right here, which contains the 4 LDRs, is used for the tracking, is used to keep the solar panel aligned with the sunlight. Now this has been designed this way so that when the sunlight is coming from, say, the position in which I'm placing the camera, the rays fall here and then cast a shadow on this side. So these 2 LDRs will provide a lower value of voltage output than these 2 LDRs. And the system, which is basically the microcontroller, will know which way that, since these 2 LDRs have a higher value, then it will rotate itself about z-axis in this direction here, because the sunlight was higher in this direction. Okay. Now, similarly, if the sun rays are coming from here, the top 2 will show that there are higher value in this portion, and this motor will activate, which will cause the solar panel to rotate about this axis in this direction, and therefore the panel will align itself with the sunlight. Okay. Now, the other parts of the mechanical system which make our system, a little good looking are you can see these pipes which contain the wires that are going inside this waterproof box. Now this box contains our circuit, which will be explained in the electric circuits part of our video. And all of the wires, all of the sensors, these wires coming from the stepper motors, they go inside the pipe and then boom, inside this waterproof box. The wires that produce the output of the solar panel coming here, and then they go inside the box as well. Now, we didn't purchase a battery, so we're using this old car battery to power our system. That's the only dirty thing about our project, otherwise it looks pretty nice and clean. And see these wires from the LDRs, and what you see here, this pipe, is a modified version of the sprinkler. The purpose of the sprinkler is, so we can clean the panel by ourselves using the app that we have designed on the platform called Arduino IoT. What we do is that we open the app, there's a button there, we press the button, and then this motor right here, it turns on via a signal from the Wi-Fi, and you can see that water will sprinkle itself right here in the demonstration part of the video. So I think I've explained sufficiently enough all that there is. I'll give you an overview again at the end of this portion of the mechanical structure. You see this is the entire frame. The rectangular frame was made first, and it is placed inside this U-frame. The U-frame is then itself connected okay, I forgot to explain this part at the beginning. This is very important. Now what you see here is the hub of a vehicle, which basically contains groups of thrust bearings, so that we can get a free rotation about z-axis. And the more the weight on this, the lesser the bearing friction. And now this hub is connected to this part to this part, and this part is connected to the U-frame. Now these teats are connected to the worm gear assembly via this chain. This is basically what we see in the bicycle. The chain and this whole assembly. we connected these two together to get the z-axis rotation. You can see the washers have been placed here so that when the system moves, the chain doesn't, collide with the frame. Now initially you can see this white patch here. This is where we placed the flow sensor, but since it's a Hall effect sensor, it was being affected by the magnetic fields that were being produced in the stepper motor's operation. So now it has been placed here, and whenever high winds come, this thing rotates, produces a voltage, and then boom, our system aligns itself horizontal to the floor, which is so that the surface area perpendicular to the wind is the least surface area. Now this was the practical setup. I think I've explained thoroughly all of it. If you still have any questions, you're welcome to ask. First, let's see the physical dimensions of the system. Now, the width of the system is approximately 8 feet 9 inches, right here. Okay, now let's measure the height. Now, for the height, let's lock the tape right here, and we pull it up all to the edge, and 4 feet 6, approximately 7 inches. The box itself has a rubber outlining, as you can see here, this black thing over there, so that it becomes waterproof when we close it from over here, and the nut bolts go in these holes. When it's bolted down, these also contain rubber washers, so all these holes also become waterproof. This way rain or any weather factors do not affect our system. Now, in this part of the video, I will explain the actual physical circuit which exists inside the box, the waterproof box. Now, inside the box, you can see this is the PCB which we got from JLC. This is the L298 motor driver which controls the water pump. And this is the stepper motor driver TB6600. This is the IBT2 DC motor driver. The stepper motor driver controls the stepper motor, which rotates the panel about x-axis. This controls this DC motor right here, which gives the z-axis rotation. Now inside the PCB, you can see in the middle of it is the microcontroller ESP32 room. This is the buck controller. These resistors form part of the circuits of the LDRs and the voltage sensors. These LEDs here, this LED here indicates if the circuit is powered on. Now there are separate sockets for ground. This entire socket, which contains 10 ports, is for ground. Behind it, where this red wire is going, this right here is the socket for all the devices that get 5 volt. This here at the edge of the board, these 3 wires are for the controlling of the stepper motor. These 2 wires, the white ones and the white and the gray ones, these 2, they control the DC motor. The circuit is a little bit messy because I didn't have time to clean it. Right over here goes the SD card module, which logs the data. This is the buck converter, which steps down the voltage from the battery, which is approximately in the range of 13 to 11 volts, and it gives us the output of 4.7 volts, so we can operate this ESP32 and all of the other circuit elements which take 5 volt as high input without using an external source. So this was the physical circuit, and it's fairly simple but also fairly effective. All of the pins of the ESP are basically being used because we're using 2 voltage sensor channels, 2 channels for the current sensing. It takes 4 pins for the LDRs, and then there's the pins of these motors, the TB66 stepper motor, the IBT2 motor, and the L298 driver. So, and all of the microcontrollers pins are effectively utilized to achieve the desired output.
Assalamualaikum, I am AQUIB Mahad. I am going to explain my code of final year project. First, I have included libraries for the SD card and EEPROM and libraries for ESP32 regarding to the EEPROM size, which I have defined 512 kilobytes. These are LEDC channel 0 and 1 for DC motor. I have defined the timer as 13-bit timer and frequency is placed to be 5000. SD card pin is defined to 5, and for hibernating the project, for the hibernating the tracker, I have defined deep sleep time 10 minutes. First, the step DIR 1 pin, step DIR 2 step pin is for the stepper motors. The NDR is defined as the upper right, upper left, bottom right, bottom left. Current sensor pin is defined to 2. The pump is at pin number 22. These are the values 4700 ohm and 100 ohm for voltage sensor. The right PWM output is defined to 14. Left PWM output for DC motor is defined to 21. And I have mentioned the value of DC default to 90 for DC clockwise. Go 20 above and it will be 110, and for counterclockwise it will again minus and it will be 70. These are the step limit is 113 and its default value is 100. These are the top left, top right, bottom left, bottom right is defined to 0. These are according to the LDR sensor. The string data message is storing for the SD card data. All of them are stored in float, sensor value, current, average current, voltage, current, conventional, and final current, etc. This is related to the flow sensor that we are using as an anemometer in our case. As it is ESP32, so we will LEDC analog write instead of only analog write here. The channels are defined here. This is function for the sleep. The pin modes are defined as an output, input for LDR, pump, and DC motor here. Current sensor is also defined. This will again store the values in plus plus. This is for the Arduino IoT. This is shown here. All of that code created is here. The PWM is for DC motors here. Here I have defined if the flow rate is greater than 4, then here I have used the if else statement. If wind is equal to 0, there is no wind, then it will calculate the values in a loop of 10. Then it will change that values in the float values. Then we will take average values of the sensor, for example, top 1 plus top right. These are the average values for top left, top right, bottom left, bottom right, top left, bottom left, top right, bottom right, and again on the basis of these values, the decision will be made whether to move the solar panel clockwise, counterclockwise, and also for the vertical axis. For stepper, if the average top values are greater than average bottom, I have added +2. These are These are the calibrated values as we have taken from the serial monitor before, and we have organized the code in that way. The stepper will move clockwise, stepper will move counterclockwise. This is for the vertical axis. And for left and right, that is the horizontal axis. If the average left greater than average right plus 1.5, then it will move DC, it will rotate it counterclockwise. If average left values of LDR sensor plus 1.5 is less than average right values of LDR sensor, it will move the solar tracker to clockwise direction. These are variables for the stopping the motor. The values of the current position of stepper and other values are printed here in the serial printer and towards the serial monitor. This is again for the calling of Arduino IoT. From the app for the pump change, if the button is pressed for one, the pump will the sprinkler will on towards the solar tracker. This is for the switching of the solar tracker to on and off the solar tracker. This is again function for the DC counterclockwise and DC clockwise. And this is function for the stepper clockwise and stepper counterclockwise. First I have made high and low, then again I have changed the pins to low and low to move the solar tracker in clockwise direction and counterclockwise direction. This is for the counterclockwise movement of solar tracker. It will initially take values, and I have set the limit to 100 the code. It will not move more than the values I have defined in the code previously by hit and trial method. This is for the SD card. Show if the show card mount failed if the card is not being inserted. We'll save the file in the SD card. It will write the values of voltage current in the SD card file. This is for the current sensor. It will take 50 values for the current sensor, and again we will convert these values, and later we will take the average of these values. Also for the current voltage, I have used the voltage divider rule here. This is the offset given to the current sensor values. This is the calculation of power E into I. This is regarding to the anemometer that is being used as a flow sensor. This is for the Arduino IoT cloud that we are being used that we are using for the solar track. I have given my SSID pass and key to the Wi-Fi to connect it towards the Wi-Fi. I made float voltage, pump and system switch. This is from my side. This is the explanation of the code that is being used for the solar tracker.
My name is Mahad and I will be explaining the whole schematics and circuit diagram and PCB of our project, that is energy harnessing through solar tracking. So our main controller is ESP32 and we have all these components. We have flow sensor, we have DC motor, we have stepper motor, we have SD card, and we have DC motor, like that is pump, and we have buck converter, and we have the whole LDRs that will help us in tracking the sun, and we have two sensors that are current sensor and two sensors that are voltage sensor. So first we have the ESP. It's a dev kit module and it has 32 pins, and these are all its IO pins. And first I will tell you about the buck converter. Buck converter is it is doing. It is getting the 12 volt supply from the voltage charge controller. My name is Mahad and I will be explaining the circuit diagram, schematics and the PCB layout of our project, and that is solar tracking. My name is Mahad and I will be explaining the schematic, the circuit diagram and the PCB of our project, and that is energy harnessing through solar tracking. So our main controller is ESP32 and that is 32 pin dev kit module, and it has 32 IO pins. So first of all, let me tell you about the buck converter. What buck converter is doing, it is converting the 12 volt supply coming from the charge controller into the 5 volts, so we can use it with the ESP and the other components. So now coming towards the main thing of our project, and that is the LDRs that are responsible for the tracking of the sun. So we have this connector over here that will be connecting to the 4 pins of the LDR coming out of the LDR module. So we have 4 resistors over here that are 100k each. We have grounded each terminal of the resistor, and we have connected the other with the IO pin and the LDR. So we have used 4 IO pins, that is IO32, IO35, IO34 and IO33. So the solar tracking will be done according to the LDRs and the signals coming from the LDRs, and we will read these values from these 4 IO pins. Now coming towards the stepper motor, how it is working. So we have this setup for our stepper pins. We have connected 3 signal pins for our stepper motor, that is IO25, IO26 and IO27. Now we are providing the power to our stepper motor by the help of our 12 volt supply, and we have grounded one end and we have provided 12 volts on the other pin. So we have this connector for the SD card. We have used IO5, IO18, IO23 and IO19 for the signal pins, and we are powering the SD card module with 5 volts. So now for the DC motor, the DC motor we are using is only using 2 pins for the signals, and that is IO14 and IO21. So the flow sensor, it is basically the anemometer that we are using in our project, because it is a modified version of a flow sensor. So that's why I have flow sensor over here. It is actually the anemometer in our project. So it is only have one signal pin, and that is iode 30, and that is connected on the iode 36, and we are powering with 5 volts. So the pump we are using is controlled with the help of a L298 motor driver, and that is having one signal pin, and that is IO, and that is connecting to the IO 22. So now the sensors we have two current sensors that is that are powering from 5 volts, and we have one signal pin for each of them. We have IO for 4 for current sensor 1, and we have IO2 for current sensor 2. Now we have two voltage sensors. So we have a current voltage divider rule over here, and we are converting the voltage coming from the voltage sensor into the more readable form, so our ESP can read the values. So here is our two voltage sensors. Now we have two strips for our 5 volt and ground, so we can power anything if we want to. Like if we want to power another module, we can do it from here. Now we have DC motor driver. We are powering the DC motor driver with 12 volts, and that it will be connected on this connector, and we are powering our whole PCB with the 12 volts. So now I will be explaining the PCB layout for you, and here we have the whole PCB layout. So over here we have the ESP32, and it is all connected to the other things. So we have these 1 2 3 4 5 connectors that will be connected on the PCB. So it is a bit confusing, so I will show you the 3Ds of our PCB. So this is the file viewer of the website that we have ordered our PCB from, and that's GLC PCB. So if I will just show you how our PCB looked when we ordered it, we have this top and bottom, we have this 3D, and I will show you some photos of our manufactured PCB. And this is our manufactured PCB that we got it from the GLC PCB. So this is our fabricated PCB that we ordered from GLC PCB. We designed and ordered it through GLC PCB, and this is the unsoldered PCB after we soldered it. These are the whole components. We have the resistors, we have one LED that will show us if the buck converter is working or not, and we have this buck converter. We have 5 connectors for all the voltage sensors and stepper driver and motor and the other things, and we have the STR female header here, and we have the female headers here for the ESP. So this is our whole PCB that we have set up in our project.
Now everything else has been explained in the other videos. This is the Arduino IoT Cloud app, which has 4 tabs. One is which switch off the controller. This is the water pump, which I will demonstrate now. This is the panel output. There's a little bit of offset in the microcontroller. This is what you see here is basically 0. It's 0 because the current sensor terminals aren't connected. This is the battery output, which constantly updates itself as soon as the Arduino Cloud update command is executed. Now I will press this button right over here, water pump, and you can see that water starts coming out of here because the pump at the bottom is now functioning. And when I stop pressing this pump, the water stops. This is how we can control the water pump using this Arduino IoT Cloud app. I'll demonstrate it over here as well. Now when I push this button over here, this pump will start to make a little bit of sound. It may be audible in this clip. Okay, so that was the end of the water, and this is how we monitor the output of the panel, output of the battery, and operate the water pump using IoT Cloud.